Welcome to Chem 432. I'm super excited to share with you. Uh, we're going to start off by thinking about what you know about water. So, um, this class is unique in that it provides an opportunity for you to connect your relationship with water, the water that you see every day, um, as well as the invisible water. So, how we grow our food, what we use to produce our clothes, and then the water footprint itself. So if you want to check that out, those are really great resources. It's really not just the water that we drink. So about 1,800 gallons of water are needed to produce the cotton that's in a pair of jeans. About 400 gallons is used to produce the cotton that's in a shirt. And it takes about 39,000 gallons of water to produce a car, including tires. So there's the water that we see, right? And then there's the invisible water, what's used to make our clothes, and also the water that's used to produce food. So one California almond has an average water footprint of about 3.2 gallons, which is really staggering when you think about, um, a handful of almonds as a snack. So, welcome. Super excited to have you here for Chem 432. Um, One of the pieces that I thought would be super helpful for us is just to talk briefly about the power of water in our society. This is an iconic image. Um, are there other um, ways that water shows up for you that you think it's present or that you notice? Hi, Megan. Hi, Jackie. So what's an iconic image of water um, that you think of?
The ocean.
Yeah, right? It's such a powerful visual for sure. I think too about um like Lake Shasta or some of the other like really beautiful kind of like on a still morning where it's like so smooth that it reflects the mountains, right? It can literally almost be like a mirror. So I think there are lots of ways in which water shows up um, in our society through art, through music, multiple ways that hi Reese, um, can be really powerful for us. So there's a context to water, and that's certainly true for California. Um, this does not work while we're on Zoom. However, you have access to these slides, and I would love for you to try the River Runner app. So it allows you to follow a droplet of water from wherever you choose to start, and then it follows its watershed all the way to the ocean. It's fascinating um, and a really great way to see how water moves. It's worth saying that water in the state of California is considered a human right. So, OEHA is um, a reporting agency that actually reports on the quality of water. Believe it or not, there are places even fairly close to CSUMB that have not had access to clean water. They actually have to use bottled water in order to have safe water to drink. Water in the United States doesn't always respect borders or state lines. In fact, there are a number of states that are influenced by the Mississippi River, even though um, they, right, aren't necessarily adjacent. So to show you that, I want you to take a look at this map. What do you notice? What's something that you see?
The Mississippi goes through like seven, eight different states.
Right? It's a huge river. But there are other ones too. Like I'm staggered by the Columbia or the Snake River. Like it literally goes east to west, which is a strange thing, right? I think of rivers typically running north south. The other piece about this that I think is really interesting is we can talk about water in a global context too. So um, everyone should have access to clean water. And there are a number of really cool projects looking at watersheds across the world, and places that are looking at the water footprints of countries. So we'll have a chance to explore that a little bit later on. But our focus today is going to be thinking about colligative properties. So you had three kind of short reads that hopefully primed you for the content that we're going to be covering today. So, big idea here is that colligative properties are going to be characteristic of solutions, and it only depends on the number of particles, not their identity. So, we're going to look at four different colligative properties. We're going to look at freezing point depression, boiling point elevation, vapor pressure, and osmotic pressure. And we're going to look at the calculations for those. And then you'll have an opportunity with your pattern of inquiry to kind of take those concepts and apply them. So the first one we're going to take a look at is boiling point elevation. And I think most folks are familiar with this in the context of like boiling water for pasta, right? Like if you add salt to the solution, it's going to increase the boiling point and make it faster to cook your pasta. So if we think about that just um, with a couple of examples. So let's say that I had a 1 molal. So molal is, right, moles per kilogram of solvent. If I had a 1 molal NaCl solution in water, so similar to what you would do if you were making pasta, right? That would increase the boiling point by 101 degrees Celsius. And if you think about that, right, that's probably not going to necessarily do all that much for you when you're cooking your pasta. But if you did a 5 molal, it would be 105 degrees Celsius. And then, right, if you did a 10 molal, right, it would be 110 degrees Celsius. And the reason that's going to be important for us is, right, as we're thinking about um, the way that these characteristic changes occur, the more particles that we're going to have present, the greater the increase in boiling point of the solution. So we have an equation that we're going to use for our boiling point elevation, and that's delta T is going to be equal to KB, which is unique, right, for each solvent. So in this case, there's a unique KB for water, times little m, or molal, times I, which is the Van Hoff factor. So we're going to take this apart. So the value for KB for water is something that you could look up in a table, right? You don't have to necessarily remember it off the top of your head, but it's going to be 0.51. And then usually, right, if we're thinking about that, um, that's specifically for water. Um, and then the other piece of this that I think is really helpful or useful, right, is, right, molal is moles or molality, which is moles per kilogram of solvent. So you're probably familiar with molarity, and we will use that when it comes to osmotic pressure. But for now, um, molality will be moles per kilogram of solvent. Solvent in this case is water. If we were thinking about our sodium chloride, that would be our solute. Okay, so let's talk about this I value or Van Hoff. So when I partition a molecule into its respective ions, I is the number of ions that are generated. So sodium chloride is going to generate how many ions? Two. Yep. Right. And so, right, if we were doing this calculation, then it would look something like 0.51, right? If I wanted to figure out my molality, right, I could figure out the number of moles of my sodium chloride, right? So if you think about that and you're looking at a periodic table, right, your molar mass of sodium is 23. The um, Cl has a molar mass of 35.45, right? So you could then, if, say, for example, you had 1 mole per kilogram of solvent, right? This number would be 1, and then I would be 2. And then from a calculator standpoint, so it would be 1.02, and that would be the change in degrees Celsius if you had 1 mole of sodium chloride. All right, so let's see if we can do a practice problem then um, that has a different Van Hoff factor. So let's say we had 152 grams of Na2SO4, and we had 875 grams of water. And I want to know what is the boiling point. So there's a couple of things we're going to have to do. The first thing is, right, we're going to think about for this molecule, right, we want to know what the I value is, or the Van Hoff factor. So from an ion standpoint, right, we get 2 sodiums and 1 SO4. So I in this case would be what? 3. Yep. Okay, so then what's the next step in our process? We've got mass of a solute. We've got grams of water. What is a good next step for us?
Moles and molarity.
Hmm. Yep. So we need to know, right? The molar mass of sodium sulfate is 142.04. So we can take our 152 grams, we can divide by our 142.04 as the mass in grams per 1 mole. So we have 1.07 moles. Now that we know the moles, what do we have to do to the water, or the amount of water that we're given? Right now it's in grams. Is that the unit that we need it in?
I mean, in kilograms.
Yeah. So we're going to divide our moles by,
1,000.
Yep, so it would just be 0.875. kilograms. So that's going to give us the amount in M. So that's 1.22. And it's lowercase m. So then we could literally just take this value and plug it in here, right? And our Van Hoff in this case would be 3. So let me erase to give us a little bit of space. So 1.86. And if we think about this, right, because we assume that water has a boiling point as a pure solvent of 100 degrees Celsius, then we would add 1.86 to the 100 degrees, and that would be our boiling point elevation. Okay, questions. Let's take a moment and just ask about GOTS and needs. So give me an example of a GOT. What's something that's a GOT for you?
The KB of water.
Yep. It's useful
And
to, right,
how
have that as a reference.
and then how to calculate the increase in the boiling point.
Yep. Yep. So, right, it's really two components we have to think about. We have to figure out what our I value is. Obviously, if something has, right, more ions, that's going to increase the boiling point more. And then typically it's a calculation of the molality. Okay, so we're gonna all right, so next up, let me erase this. So now we're gonna think about the freezing point depression, which is similar to boiling point elevation, except in this case, right, we're adding solute to lower the freezing point. So probably the most common example is in spaces that have winter and ice. It's not uncommon to add salt um, in order to prevent um, freezing. So if you add salt, then it depresses the freezing point, so it's um, harder to form ice. All right, so for this one, so it's again a delta T, which makes sense because we're talking about a change in temperature. And we're going to use negative KF. There are two different schools of thought. There are some folks that don't put the negative in front, but then you get a wonky number. So I think it's better to just have the negative. And again, we're using molal. And again, we're using I. So in this case, right, depression, right, that's what the negative is. So if we add salt, we're going to lower the freezing point. KF in this case, again, is specific for water. And it's going to be negative 1.86. And that's degrees Celsius per molal. And right, the really cool part about this is, so let's say that we're thinking about a similar situation. So let's say we started out with 0 molal, it's just pure water. Well, then our freezing point is going to be 0 degrees Celsius. Um, if we had 1 molal NaCl, and granted there are lots of different salts that folks use, um, then it would be negative 3.72 degrees Celsius. And if you're thinking about this, right, like you can imagine then, right, if it was 5 molal, it would become 18, negative 18.6 um, degrees Celsius. Now, what if it was a salt other than sodium chloride? So let's say we had 5 molar, or sorry, 5 molal um, aluminum chloride. So in this case, right, because of the fact that there are four um, ions, then it would be negative 37.2 degrees Celsius. So you could, right, simply by changing your salt, change the freezing point depression. So similar concept to what we did with boiling point elevation. It's just in this case, you're depressing, right? Or it's, right, has to get much colder before the ice freezes. Okay. Um, I feel like this one is very similar to the boiling point elevation. Any questions about this colligative property?
I have like a general question,
Yeah,
like
go for it.
comment about it. So like does adding solvent to water just increase like its temperature resistance overall since it both lowers the freezing point and raises the boiling point?
Ooh, good question. Um, so water, right, by itself is a pure liquid, and so its properties without a solute in it um, will essentially, it'll be 100 degrees to boil or 0 degrees to freeze. If you added something, and that solute could be a liquid, right? It doesn't have to be a solid. Then the addition of a solute is going to change its boiling point um, and or potentially its freezing point. So some of it depends on, right? Is it something where you're putting heat into the system? In which case, right, adding a solute is going to elevate their boiling point. So let's say I added hexanes, right, to water. That's going to increase its boiling point because, right, there are more particles of hexane than there are just water. So that's a really good question. Thanks
Are
for
there
asking.
solutes that lower the boiling point, like something that maybe has a lower boiling point than water?
Ooh, so we're going to talk about that next. We're actually going to talk about vapor pressure, which is specifically related to that query. So um, let me get us there. So you probably remember partial pressure when you studied gas laws. So partial pressure of anything. So let's say it's partial pressure of water is going to be equal to the mole fraction of water times the pressure total. So let's say you have something that's a highly volatile liquid. So your question, Jackie, was, well, what if you add something, right? Can it ever decrease the boiling point of water? So Acetone is a great example. Um, it's something that evaporates really quickly. So it's not going to change the um, behavior of water as long as it evaporates quickly. If, right, it stays around, so you're in a situation where it doesn't evaporate quickly, then it's going to still increase the boiling point of water. So I don't know of a scenario in which you can decrease the boiling point of water other than by changing the pressure. So let's take a look at this one. So this, right, is the mole fraction. And a good way to think about this is it's the moles of some part, right? And part in this case could be water, it could be something else, over the moles total. So let's say we're looking at that scenario where it's, right, our sodium chloride and water. So in this case, we would figure out the moles total. So let's say that we had um, 10 grams of our sodium chloride. So it's 58.44. So if I had 10 grams of NaCl, I'm going to divide by my 58.44. And that's grams per mole. So in this case, I have so 0.711. And let's say that I had 20 grams of water. All right, and so molar mass of water is 18.02. So that's 1.109. Okay, so cool part about this is, right, for each of these, right, those are the individual mole components. So if I add them together, that's my N total. So 0.1711 plus 1.109. So 1.2801. And in this case, we're solving for water, so we're going to use the moles of water in the numerator. So that's our mole fraction. Now, we need to know our P total. So in this case, let's assume that it's just one atmosphere. So our P, H2O then, would be equal to our mole fraction. So 1.109 divided by 1.2801. So 0.866. And remember, a mole fraction has no units. And we'd multiply that by 1 atmosphere. And so this then is the vapor pressure of water with 10 grams of NaCl. So part of what I want us to think about here is um, the partial pressure of something like water can be influenced by solutes that you add to it. Um, and that can actually have a lot of implications medically, right? It can have implications, say, for example, if you are scuba diving, it could have implications, say, for example, if you're manufacturing materials. There are several different ways that vapor pressure can come um, into play. All right, we've got one more to take a look at. So the last one is osmotic pressure. So give me just a moment to erase.
So does the fact that a solvent can only increase the boiling point have to do with energy transfer?
That's a good question. So um, almost all of this is, right, the energy that it takes to, say, for example, boil water or to change it from its liquid state into its gaseous state. And so if you have more particles in your solution, it's going to take more energy to essentially move those particles
Yeah.
through Brownian motion. Um, and you have to put in enough energy so that they can escape that liquid surface layer. There's some really interesting chemistry we'll get a chance to take a look at about how liquids escape to become gases. Excuse me. But it's entirely about energy. So if it's just water, then 100 degrees is sufficient because the only thing that you have to break um, is essentially the liquid water molecule escaping to become a gaseous water molecule. But if you have something, say, for example, like a solute like sodium chloride, then, right, you have to have enough energy, right, to move those molecules and, right, um, that energy is greater than just water by itself.
Okay.
All right. So last one, and this one I think is pretty fascinating because it really ties to almost everything we know about in terms of cells, um, and the movement of water across cellular membranes. But osmotic pressure is where you add a solute to a solvent, and that pressure, right, is what's going to prevent solvent from flowing across a semi-permeable membrane. So if you want to think about it, um, a dialysis is a really good visual, right? You're moving water across a membrane, and the pressure or the osmotic pressure, right, is the resistance to flow across that membrane. So um, this one, um, we use something that kind of looks like a pi, um, but that's the symbol for osmotic pressure. And then it's capital M, so molarity, times R, which is a gas constant, times T times I. So I you're already familiar with, that's the Van Hoff factor. You're probably also familiar with R. That's 0.08206 liters atmospheres per mole Kelvin. And so in this case, though, the T is really important. We have to convert our T from degrees Celsius to Kelvin. So in order to do so, we're going to add 273.15 in order to convert. So let's do an example. So let's say that I had 2.02 grams of urea. Its molar mass is 60.06 grams. And in this case, let's say that I had 145 milliliters of water, so 0.145 liters. So my molarity then would be 2.02 divided by 60.06 divided by 0.145. So that would be 0.2319. All right, so if we're plugging into our pi then, or our osmotic pressure calculation, so it's going to be 0.2319 capital M. And then our R value is that 0.08206, and that's liters atmosphere per mole K. And our temperature in this case is 20 degrees Celsius. So 20 plus 273.15. So our temperature is 293. And urea in this case has a Van't Hoff of 1. So if we do that calculation then, it's 5.579. And if we think about this, right? So our moles cancel here, and our liters cancel, and our Kelvin cancel. So the only unit left is atmospheres, which makes sense because it's pressure. So 5.58 if we're thinking about sig figs. Atmospheres is, right, the pressure, the osmotic pressure when you add urea to a volume of water. Okay, questions. We're going to look at some really cool applications of osmotic pressure and osmolarity specifically in our Tuesday session. Okay, so let me clear all drawings, and then we're going to go and take a look at, so in your Canvas page, you've got our first pattern of inquiry. So my thinking was that we would have everything due on Monday so that essentially you would have a full week to work on a pattern of inquiry before it's due. Um, so this is intended to be a collaborative space. So I think it's far more beneficial for us to work through and talk about the ideas and then each of you are responsible for submitting. So um, I really want to encourage collaboration. So let's take a look at the first one. Um, what do you think are different ways you could represent water? I think each of you did a really great job on this um, when you submitted your concept map for what you know about water. Can anyone think of some examples?
H2O.
Yeah, right. That's a good one, right? It's the
There's
symbolic
also
representation for sure.
you can draw like a bubble diagram of the structure with a hydrogen and two oxygens.
Mm-hmm. All right, so we could do H2O, that's the symbolic. We could do a Lewis dot structure. I think that's what you're describing
Yeah.
with its two lone pairs. We could draw the polarity, right? So we could draw something like where this is a partial positive and this is a partial negative. This is a partial positive. So those are three different representations. All right. Is water a polar molecule or non-polar? How do you know? What do you think?
Isn't it polar?
Yep, for sure. How do you know that it's polar?
The partial negative and positive?
Hmm. Right? And specifically, the fact that there's an uneven distribution of electrons. So,
Yeah.
um, while this molecule has symmetry because of the hydrogens, because of the difference in electronegativity, the oxygen certainly has more of the electrons than the hydrogen does. Okay, how about number 3? What's the boiling point of a 0.33 molal solution of sodium chloride in water? So this one will have to harken back to the example we did for boiling point. So we've got delta T,
Is it
we've got our KB, we've got our M, and we've got our I.
is it like close to 100.3366?
Mm-hmm. Yep. So this would be 0.51. They gave us the 0.33 molal. And then because it's sodium chloride, we know the Van Hoff is 2. So 0.336. So it would be 100.336 degrees Celsius. Okay. Someone want to help us out? Why do we put salt on ice on sidewalks in winter?
Because it lowers the freezing point.
Yeah, right. So if we have a sudden drop in temperature, if we have salt, then it's less likely to freeze. Whereas if we don't have salt, it's more likely to freeze. Okay, ethylene glycol, EG, is a common automobile antifreeze. Calculate the freezing point of a solution that has 651 grams of EG in 2,505 grams of water. Would you keep the substance in your car radiator during the summer? The molar mass of EG is 62.01. The KF value is 1.86, and the KB is 0.52 for water. So what do you think?
Yes,
Mm-hmm.
because the solvent also raises the boiling point.
Mm-hmm. Yep. It doesn't hurt you. Cannot possibly cause harm. All right, so last one for us. Let me clear all drawings. So, um, for this one, I want you to um, choose your favorite beverage, whether that's coffee or tea or an energy drink. And I want you to do at least 4 colligative property calculations associated with your beverage of preference. So, um, a boiling point elevation, a freezing point depression, calculating vapor pressure, and then osmotic pressure.
Are
So,
we looking at all the solutes?
um, you know what? I would say choose a solute. So, for example, if you drink tea and you put um, honey or lemon in tea, then you can do something like um, citric acid or a sugar. If it's coffee, you could look at um, adding milk, or you could look at um, adding some type of sweetener. If it's an energy drink, you could look at, say, for example, the vitamins. I would say you can assume a solute that you're looking at for the purposes of these calculations. Otherwise, it gets a little bit messy. Sound good? So that should be, I think, a reasonable review of colligative properties. Um, and hopefully from a review standpoint, this helps you with both the calculations for molarity, as well as the calculations for molality. Those will need to come back and revisit. We're going to see them again next week. So, a couple of other pieces that I wanted to show you all. So my guess is you have seen this, but I just want to take a moment. So the reading quiz is intended um, to kind of help you refresh your recollection and um, kind of make connections between concepts. So um, this one I think is pretty straightforward. We've talked about this at length today. Um, you will have to read and or watch the water activity and food. That's something that we're going to be talking about next week. And then serum osmolality and how it affects cells is something that is also from the reading. So let me show you where you can find those. Um, I will keep adding to this list, but you'll notice these 3 are the 3 that you're going to need to read in order to be able to answer the reading quiz. Next week, if you'd like to look ahead, we're going to be looking at osmotic pressure, hydration, and water autoionization. Um, so that's a preview, if you will. We always have essentially a reading quiz that's a recap of the concepts that we're covering, and then a pattern of inquiry. We'll do typically a pattern of inquiry per day, so you'll have 2 that are due on Monday. This week we just have 1. Does that make sense? Okay. Any questions from folks in terms of either structure and or setup of the class?
The class ends on the 27th, right?
That's correct.
It's quite short.
It is. It's 8 weeks. So from June through
8 day.
July. Mhm. Yep. Yep. And then this class does not have formal exams associated with it. So if you want to think about the breakdown of the course structure, 60% of your grade are the patterns of inquiry. And then 10% is the reading quizzes. And then we have a water project that will start about midway through, and that will be due the final day of class. Mm, Sorry for scrolling. So here's the breakdown. Um, and we'll talk about the community water project and the associated calculations for that presentation. So, um, hopefully it's something where we have kind of a regular pattern that we follow and it becomes familiar. And then if you have questions, I'm happy to um, meet via office hours if that's convenient, or we can reserve some time at the end um, of our Tuesday, Thursday sessions just to answer any questions. So, any questions I can answer for you? Awesome. Well, I hope you have a great rest of your Thursday, and I will see you next Tuesday.
Bye.
Bye. Thanks so much.
Hi, Corinne. Sorry, I had a question. It's just not related to the,
Yeah, no, go for
yeah.
it.
But I didn't realize that it ends on the June 27th?
Nope, July.
July.
It
Oh
goes,
my God. Okay. Thank goodness.
no. It goes, it's 8 weeks. So it
Mhm.
goes through June and then July.
Okay. I was I was worried. Okay. That's all.
Yeah, there's no way. We would have to meet way more often if it was only going to be 4 weeks.
Yeah, I was
So,
about to say I don't remember my other
yep,
summer classes being like that.
yep. Nope, you're
Okay.
good. We're all set.
All right. Thank
It
you,
doesn't
Corinne.
end until July 27th.
Perfect. I was worried because I heard 27th and I just assumed June and I
Nope,
was like, wait a minute. I'm gonna
nope,
be
you're good.
in
No worries. It's okay. Don't stress. When do you leave for Vietnam?
on the 14th.
Okay.
Um, so that's what I was worried about.
Yeah, no worries. My thinking for that is, I will record just like what we did today,
Hmm.
each of our sessions. And so if you have questions, um, you can both watch the recording and we should make our way through, I would say almost all of the patterns of inquiry.
Okay.
Usually we'll get, I don't know, um, 4 or 5 out of the 6 possible questions. So it shouldn't be a problem, but I'll have those patterns of inquiry ready to go before you leave.
Thank you so much for being
Oh,
so
are you kidding? I can't wait to hear about your adventure. You'll have to come
so
back and tell me all about it.
you bet. I'm so excited.
Yeah, it's gonna be amazing. All right, well, have a
Bye.
great day and we'll see you soon.
You too. Thank you so
Thanks.
much.
Bye.